Hey guys, welcome to video 63. Today we're going to work through the homework problem I left at the end of the previous video. And what we've got is a 12AU7. We're going to set up a Q point with a plate current of 7.5 milliamps and a plate to cathode voltage of 175 volts. And then we're going to evaluate the AC characteristics for two different load conditions. We'll get to that in a minute. First things first, let's locate our Q point over here on the plate curves. 7.5 milliamps is right here. And if we come over 175 volts, our Q point is located right here on this intersection. And it doesn't fall on any of the grid biasing curves. So let's just sketch one in, see what it looks like. A visual estimation, we're between -4 and -6 volts. We're a little bit more than halfway, so I'd say that looks like about -5.5 volts. So let's just estimate our VGK at approximately -5.5 volts. Now we can find our cathode resistor R sub K, which is the magnitude of VGK, 5.5 volts, divided by the plate current, 7.5 milliamps, and that works out to be 733 ohms. And that's not a standard value, but 680 is the closest standard value below it. Then that's close enough. So let's use 680 ohms, and that'll work out fine, I'm sure. Now let's determine the plate resistor we need to make this work. That's going to be R sub P equals VPP minus VGK, and we can subtract off the drop across RK. That would be I sub P times R sub K divided by the plate current at the Q point, IPQ. So what do we have here? VPP is 250 volts minus 175 volts minus the drop across RK is going to be 5.5 volts divided by 7.5 milliamps, and that works out to be about 9.3 k ohms. And we'll just throw 10 k ohms in there, and again that'll probably work just fine. So let me fill these resistors in here. Now we've got 680 ohms and 10 k ohms, and there are the values to set up our Q point. The next logical thing for us to do is to sketch in our DC load lines, so let's do that. Our VPK in cutoff is equal to VPP, so that's 250 volts, and our plate saturation current, IP sat, is equal to VPP over RP plus RK. So that's 250 volts divided by 10K plus 680, 680 ohms, and that works out to be about 23.4 milliamps. And let's go ahead and mark these points. 250 volts is right down here. 23.4 milliamps is, well, you know what, that's pretty close to 25, and that's going to be more convenient. I'm going to put the point here right about 25. That's the current we'd get if we just had RP by itself with no RK, but that's not a problem. So let's just connect these points, and here is our DC load line. And so far everything looks good. So let's go on over to our circuit now and address R sub G, the grid resistor. Again, that can be just about anything we want. So let's just go with 1 megohm to keep the input resistance nice and high. And now let's take a look at our coupling and bypass caps. C1, again, without going into a lot of extraneous detail here, 0.1 microfarads would work well here. Now we're going to be dealing with a relatively low resistance load this time. The first value we'll work with is 18 k ohms, so we're going to increase the value of C2 to 10 microfarads, and that'll work okay in this application. And again, down here C3, we'll set that one to 100 microfarads. And we'll talk more about picking these values in another video, but for right now, this will work well for us. Okay, I've consolidated all of this messy writing and these calculations into one reasonably concise page, and here we've got the circuit with all the resistor and capacitor values we've determined, and the calculations for RP, RK, IPsat, VPK cutoff, and a neater version of the DC load line with all the pertinent points labeled. The next thing we're going to do is take a look at our small signal analysis using a load resistor of 18K ohms. So let's go on over and look at a decluttered version of this page, and we'll get to work on that now. Let's start by determining the small signal plate resistance R prime P, which is little rp in parallel with RP and RL. So that's 6.5K in parallel with 10K and 18K, which works out to be about 3.2 K ohms. Now our external R prime K in the AC small signal model is 0 because we're using full bypassing, so R prime K equals 0, and our voltage gain then is AV equals negative GM times R prime P. GM is 3.1 millimos, so negative 3.1 millimos times 3.2 K ohms is a voltage gain of about negative 9.9, and you could just call that negative 10. Alright, now let's start our large signal AC analysis. We'll begin by determining R prime L, which equals RP in parallel with RL. That's 10K in parallel with 18K, and that works out to be about 6.4 K ohms. All right, now we'll use this to determine the endpoints of our AC load line. Let's start by finding V sub PK cutoff, which is VPKQ plus IPQ times R prime L. All right, VPKQ is 175 volts plus 7.5 milliamps times 6.4 K ohms. That's about 175 volts plus 48 volts. So our VPK cutoff is 223 volts, and that's close enough to 225, so we'll just mark that over here, and we'll use red to mark that endpoint right here. Okay, now we want to determine IPsat, and that's IPQ plus VPKQ over R prime L, 7.5 milliamps. Sorry about this writing, it's hard to squeeze it in here. Plus 175 volts divided by 6.4 K ohms. That works out to be 7.5 milliamps plus 27 milliamps, and that is pretty darn close to 35 milliamps. So here's the second endpoint of our AC load line right here on the edge of our graph. Now let's connect these up with a straight line, and if we did everything just right, the AC load line should go right through the Q point, and it does. So there we go. There's our AC load line. Now, what I want to do next is determine where the AC load line crosses the zero grid voltage curve, and that's right here. And we called this voltage V sub PK minimum. And in this case, it looks like about 125 volts. And the corresponding current would be I sub P max. All right, so that coordinate looks like about maybe 15.5 milliamps. Okay, 15.5 milliamps. Now what we want to do next is determine our output signal clipping points. So let me make a little bit of room down here, and we'll finish up our calculations here, finding VO max, which is equal to IPQ times R prime L. That is the distance from VPKQ over here to VPK cutoff on the AC load line. And rather than write that out, I have the calculation here. IPQ times R prime L is about 48 volts. So the distance from here to here, 48 volts, pretty close to 50. How about let's just round that off and call it 50 volts. Okay, VO min, that is our negative output clipping voltage, is the distance from VPKQ to VPK minimum, and that's going to be also about 50 volts, right? VPK min was 125 volts, so 125 to 175 is 50. So that's going to be about negative 50 volts, and there is the completion of our small signal and large signal AC analysis. Now I'm going to consolidate all of this into one neat page, and let's go on over and take a look at that now. Okay, here we are, and rather than repeat all the calculations, I just listed the equations I used to get the results we arrived at here. And I've also labeled all the pertinent points on the DC and AC load lines. And keep in mind that if we overdrive the amplifier and the Q point moves to the left past VPK minimum, we're not necessarily going to get clipping on the negative going output, but we could get significant grid current flowing, and we want to avoid that. And also, if we look at the AC load line, notice that we can get some pretty high plate current flowing if we really overdrive the amplifier. We could get up to 35 milliamps on negative going output peaks. So let's check the data sheet just to make sure the 12AU7 can handle this okay. And if we go down to the maximum rating section and we go down there to the peak cathode current, we see its maximum value is 60 milliamps. That should be more than enough for us, but you have to keep in mind that cathode current includes plate current and grid current. And if we're driving the grid positive with respect to the cathode, we could get some grid current, but it's not likely to be that much in the typical application, so we should be okay here. And if we look at the rating above this, the DC cathode current maximum value is 20 milliamps. That would be the maximum IPQ value that you would want to set for your design, and we're at 7.5 milliamps, so we're okay there too as well. Okay, so that concludes the first half of the homework problem. Now we want to see what happens if we increase the load resistor to 470 k ohms. So let's go on over to the next page. And rather than going through all the calculations by hand, this time I'm just going to present the results. It'll speed things up a bit. And if we come over here, we see R prime P is 3.9 k ohms. R prime L is 9.8 k ohms, and our voltage gain now is -12, so we've got a bit more gain than we did in the previous example. Now, VPK cutoff for the AC load line works out to be 249 volts, and that's almost identical to VPK cutoff for the DC load line. And that makes sense because RL is so large compared to RP that we're going to have very little difference. And actually, the DC and AC load lines are so similar that I really probably wouldn't do a separate AC load line, except that we're doing it here for the exercise, so we're going to continue. But anyway, we've got a VPK cutoff of 249, so I'm going to mark that over here. And our IP sat works out to be just a little bit more than we had for the DC load line. It's 25.4 milliamps versus 25. So let me put a point here, some that looks like it might be 25.4 milliamps. And let's connect these points. And here is our AC load line, and it does go right through the Q point as we would expect. And again, it's so close to the DC load line that normally I wouldn't even bother with this, but let's just go on and continue. All right, our VPK minimum value, that is where our AC load line crosses the VG equals 0 volts curve, is right here. Let me get my pencil back on. We'll mark that point again. And if we come down here, that looks like about 112 volts. Okay, so if we mark that off, that would be 112 volts. And IP max, based on this value, looks like about 14 milliamps, and that's what I've listed over here. Okay, now calculating our maximum output value based on the AC load line, it's basically the distance from the Q point over to VPK cutoff. So that's about 74 volts, and VO min would be the distance from our Q point to VPK minimum, 112 volts, and that works out to be negative 63 volts. All right, and again, I've consolidated this into one neat diagram, so let's go take a look at that. And here we go. Now I've labeled all the pertinent voltages and currents, and because I love you guys, I also included the curves for the case where RL equals 18 k ohms, so you could compare them easily. Now let's go on over and we'll look at the tabulated values, and this matches up with the table that I presented at the outset of the problem statement. So the only thing left for us to do now is to take a look at the experimental results and see how they compare with these theoretical values. Okay, here's our circuit, and I put the theoretical values over here in blue boxes. The experimental values are in red, and I also put them over here in a table. And as you can see, the experimental values match up pretty closely to the theoretical values, and I built the circuit using several different 12AU7s and equivalent tubes, and they all came up pretty much the same. So we have really good agreement here with our theoretical values as far as the Q point goes. Now let's see what happens with the AC signal analysis. Now we started with RL equals 18 k ohms, and I applied an input voltage of 1 volt peak to peak at 1 kilohertz. That gave us an output of 9.3 volts peak to peak with phase inversion. So our voltage gain is negative 9.3, and that compares pretty well with our theoretical value of negative 9.9. Now it's interesting to see what happens if we increase the input voltage. So I increased V into 10 volts peak to peak, which is about the maximum we can apply without driving the grid positive with respect to the cathode. That gave us an output voltage of 83 volts peak to peak for a voltage gain of negative 8.3 versus the theoretical value of 9.9. So our voltage gain does drop a bit, and that's because of the nonlinearity of the output signal. You can see the gain to negative going inputs is less than the gain to positive going inputs, resulting in the squashing and stretching effect that we also saw with bipolar transistors and field effect transistors in this Class A amplifier configuration. Now, I also did a spectrum analysis on the output, and these are the results I got. As you can see, we're getting a lot of both even and odd harmonics coming up in the output signal here. And again, the scope is expressing the output here in dBV. That's decibels referred to 1 volt RMS. So our fundamental is 29 dBV. The second harmonic is 9 dBV. The third harmonic is -7 dBV, and so on. Now, one of these days we'll do a cool comparison of the distortion characteristics of tubes versus JFETs and MOSFETs and BJTs, but that's a topic for another day. So let's go on over and take a look at the results we got with a load resistance of 470 k ohms. As in the last experiment run, I started with Vin equals 1 volt peak to peak at 1 kilohertz, and this time we got an output of 11.7 volts peak to peak, phase inverted, so our gain is negative 11.7. Theoretically, it was negative 12, so we're really close again. And everything looks really good. So now I'll increase the input voltage to 10 volts peak to peak. Again, that's the maximum input we can use without driving the grid positive with respect to the cathode, and we get 105 volts peak to peak out for a gain of negative 10.5. Again, that's pretty close to our theoretical value, but it's a bit less than we had previously because of the asymmetry of the output waveform. The positive peaks are smaller than the negative peaks, and again, that's to be expected from this kind of amplifier. And that wraps it up for today's video. I didn't bother running a spectrum analysis on this because it's very similar to the previous results we got. So we'll continue with our vacuum tube studies in the next video, and I'll see you then.